Hello everyone, my name is Ying Yi, and I'm a PhD student from KU Leuven. This is a recorded talk of the joint work with Xi Shen, Shao Shihu, and Johan Soikens named Boosting Co-Teaching with Compression Regularization for Label Noise. The aim of this paper is to derive image classification models in the presence of label noise. The learning task is driven by the fact that large-scale, high-quality annotated data has contributed a lot to the prosperity of deep learning, but their collection procedures are usually expensive and time-consuming. In contrast, imperfect data, such as those with noisy labels, are both cheaper and more available. Efforts have been made nowadays in the deep learning community to derive models able to compete with label noise. The existing paradigms include adding regularization to constrain noise, estimating the label transition matrix, training on the selected samples or reweighted samples, which are usually considered as clean annotated data, and conducting label correction. However, among those methods, those achieving state-of-the-art performances may require an appropriate tuning on multiple hyperparameters. In this regard, we consider deriving a model that is both simple and strong. In this paper, we achieve this by combining regularization with training on selected samples. To be specific, on one hand, we revisit a compression regularization called the nested dropout. It was originally proposed to learn ordered feature representations so that it can be used to perform faster information retrieval and adaptive data compression. On the other hand, we consider one widely acknowledged method called co-teaching. These two serve as complementary to each other, and their combination helps us to achieve comparable or even better performance than the state-of-the-art approaches on two benchmark real-world datasets named Clothing 1M and Animal 10M. Our code is now available on GitHub. Here's the workflow of the nested dropout. We assume that H is a hidden feature of the network. In each training iteration, we only keep its first k-dimensional feature and mask the rest to zeros, where k is sampled from a categorical distribution. In this paper, we consider a Gaussian categorical distribution. By training with the nested dropout, we are able to learn ordered representations where the front channels contain the most important information, while those on the back contain the least. For co-teaching, two networks train simultaneously where they update themselves based on the small loss instances selected by the peer, since their samples have higher probabilities to be clean. The combination of them comes with two steps. In the first step, we train two networks independently with nested dropout. In this manner, they are able to learn to separate the most important dimensions of the representation from the rest. In the second step, we use these two methods to co-teach each other based on their most confident predictions. The final performance is the accuracy of the ensemble model. Before we go to the real-world dataset, we first verify that nested dropout is indeed able to resist label noise by a toy regression experiment. Here, MLP with standard training is the baseline, and we compare it with MLP with nested dropout. It can be seen that MLP overfits to the label noise, while nested with the first 10 channels recovers the ground truth Y better. However, with the number of channels increasing, nested gradually overfits to the label noise due to over-parameterization. This demonstrates that the first few channels in a nested network contain the main data structure information, while channels towards the end are more likely to encode misleading information that would overfit to the noise. We compare our method to the state-of-the-art approaches on Clothing 1M. It is worth noting that this table also includes very recent approaches such as divide mix and PLC. Our single model with nested dropout not only surpasses the standard dropout, but also achieves comparable performance to pencil and MLNT. Incorporating co-teaching further boosts the performance to 74.9% and outperforms the state-of-the-art divide mix. Here's the experimental results on Animal 10N. Note that our best performance by using nested dropout and co-teaching achieves 84.1% accuracy, outperforming the recent approach PLC. We also provide the ablation study of sigma nest on Animal 10N, which controls the compression rate of nested dropout. Nested dropout provides consistent improvement compared to training with standard cross entropy, and the performance gain is also robust to the choice of the hyperparameter. It's worth noting that models trained with nested dropout achieve better performance, but with only less than 1% of the channels comparing to the models trained with standard cross entropy. To conclude, we investigated the problem of image classification in the presence of noisy labels. Specifically, we first demonstrated that a simple compression regularization called nested dropout can be used to combat label noise. Moreover, due to its simplicity, nested dropout can be easily combined with co-teaching to further boost the performance. We validated our approach on two real-world noisy datasets and achieved state-of-the-art performance on both datasets. The proposed approach is simple comparing to many existing methods. Therefore, we hope that our approach can be served as a strong baseline for future research on learning with noisy labels. In the end, I would like to thank my collaborators and supervisor, and thank you everyone for your attention.